A very important piece of evidence for the Big Bang cosmology is the presence of an almost uniform cosmic microwave radiation that can be explained with Planck's radiation law. Max Planck's radiation law, proposed first in 1900, marks also the commencement of modern physics and is important in other contexts. For example, it also describes the radiation of the sun, the radiation of an incandescent light bulb, and of all radiators that have a constant temperature. The graph shows the spectral radiance, the intensity of light from such a radiator with constant temperature, as a function of wavelengths here quoted in micrometers. The red curve shows the result for a temperature of 3000 Kelvin, green is 4000 Kelvin, and 5000 Kelvin is close to the temperature of the sun, and you can see that the maximum intensity range agrees well with the wavelength range of the visible spectrum of light. The cartoon on the right illustrates the idealized concept of a black body radiator. The concept considers a cavity that is effectively closed so that light inside cannot escape. It also considers that the light is not reflected, but is always fully absorbed at the walls and can only be emitted. The cavity is kept at a constant temperature. Interpreting this concept classically gives the black curve in the graph, which is shown here for a temperature of 5000 Kelvin. This classical theory does not agree at all with the measured radiance coming from the sun, or for that matter with the intensity spectrum measured for the cosmic background radiation. In this presentation, I want to discuss the virtual black body radiator and the concepts that underpin it, and see how these concepts can explain the cosmic microwave radiation that we measure, and that is a very important piece of evidence for the Big Bang model of the universe. The discovery of the cosmic background radiation was entirely circumstantial and by chance. It occurred in 1964 and was carried out by Arno Penzias and Robert Wilson with the Holmdel horn antenna in New Jersey, of which I show an image in a moment. Penzias and Wilson discovered a relatively intense background at microwave frequencies with their antenna that, interestingly, was uniformly coming from all directions. The fact that this is a uniform signal, that is direction independent or isotropic, suggests that it should not be associated with a particular stellar object, but with the entire universe. The photo shows the two discoverers underneath the Holmdel horn antenna. It is apparent that the antenna can be turned 360 degrees in the vertical and also 360 degrees in the horizontal. That's really important because it allowed to confirm that the 2.7 Kelvin background radiation, as we call it today, was coming almost uniformly from all directions of the universe. Initially, Penzias and Wilson thought that their detection was a dirt effect, noise of the instrument, instrumental in nature, and they cleaned the antenna, even thought that pigeons might be responsible. However, finally they accepted that the signal was truly coming from the universe. In 1978, they received the Nobel Prize for their discovery. Here you see the result by Penzias and Wilson together with more recent measurements of the cosmic background radiation. Plotted is the brightness versus the wavelengths and the frequency of the radiation on a log scale. You can see that these very independent measurements from satellites and laboratories and balloons agree very well with each other, and they also agree with the superimposed curve based on a 2.728 Kelvin black body. The original Penzias and Wilson result of 3.5 Kelvin had an uncertainty of plus minus 1 Kelvin for the associated temperature of this black body. The precision of the more recent results confirms that the background radiation is that of an ideal black body. The measured cosmic background radiation is significant in two ways. It is almost uniform and independent of direction, and it confirms perfectly with the spectrum expected for an idealized black body. The black body spectrum of the cosmic background radiation is just interpreted as electromagnetic radiation that decoupled from the Big Bang and the expansion of the universe at about 380,000 years after the Big Bang singularity. Further confirmation of this spectrum has since occurred through measurements with the satellite COBE and more recently the Wilkinson anisotropy probe WMAP. The recent measurement of slight anisotropies, slight variations in the almost uniform background radiation spectrum, is important since an entirely uniform cosmos could not have generated galaxies as we observe them today. However, the anisotropy is a tiny effect in an almost uniform radiation. On the left you see a cartoon of the COBE Cosmic Background Explorer satellite. At the bottom visible are the solar panels which power the instrument, and at the top is the shielded and cooled radio frequency antenna. The result of the COBE measurements are shown on the right as intensity as a function of wavelength in millimeters. The excellent agreement between results and the red FID for a temperature of 2.74 Kelvin confirm that the background radiation conforms with that of an ideal black body. This view graph shows the improvement in precision that has been achieved since the original measurements of Penzias and Wilson in 1965. In these plots shown on the right, going from the left to the right, corresponds to a rotation about one's axis of 360 degrees, and going from the bottom to the top corresponds to a similar rotation in the vertical direction. The plots just cover all directions as visible from Earth, the entire sky. The tiny variations in the background radiation, as in particular visible in the WMAP plot, are crucial input to our models of galaxy formation. The variations of the plot show that nucleation sites could have existed, which allowed gravitational pull to start and create stars and galaxies. The presently measured spectrum of the cosmic microwave radiation corresponds to a black body spectrum for a 2.7 Kelvin black body. Since the universe was much smaller in earlier times, and therefore the energy more dense, we expect that in those times the temperature of that spectrum was much higher. And we can trace this back to the time of 380,000 years after the Big Bang, where photons and electromagnetic radiation decoupled from matter. The idealized black body radiator is not only a great model of the entire universe, it also describes other radiators of electromagnetic radiations really well. A second very important example is that of the Sun. Shown here is the spectral irradiance of the Sun as a function of wavelengths, covering 250 to 2500 nanometers. Shown is in yellow the sunlight at the top of the atmosphere, and shown in red the intensity of the sunlight as it is measured at sea level. The difference is the absorption of light in the atmosphere, which is particularly pronounced when certain molecules are excited. Indicated here are O2, water, and CO2. In the discussion of global warming, the interplay of sunlight interacting with the atmosphere and reflected radiation from the ground that is absorbed and reflected by the atmosphere is of crucial importance. The grey curve shows a 5250 degrees Celsius blackbody spectrum. This theoretical curve agrees rather well with the intensity measured for sunlight at the top of the atmosphere. It is clear that also for this system, the idealized black body is a great theoretical model. It is remarkable that the black body model describes the radiation of the entire universe, that of sun and stars, that of a coal fire, that of an incandescent light bulb, just as well, although it is an idealized closed cavity that cannot really be fully realized in a laboratory. Moreover, as we will see, the black body radiation emitter is a manifestation of quantum physics in nature. In fact, it was the first physical system where quantum effects were deliberately introduced in the description of nature. Let's look at the concepts of an idealized blackbody radiator in some detail. The cartoon on the right sketches some of the important aspects of this concept. A cavity is effectively closed, it is kept at a constant temperature, and its walls emit radiation. This radiation travels through the cavity and hits another wall. By definition, this light cannot be reflected, therefore the term black body, black-walled body radiator. The light is absorbed, and after a while light is emitted so that the system is in thermal equilibrium and the temperature is maintained. The cartoon on the bottom left emphasizes the importance of the wall of this blackbody radiator. At this wall, thermodynamics and electromagnetism meet. In fact, they are linked. The idea is that the temperature, and that is thermodynamics, of the wall is maintained through the molecular motion, the vibration of its atoms, and that includes also charge carriers like electrons and the core of an atom. So we have moving charges. Moving charges, as we know from electromagnetism, create electromagnetic waves which are therefore emitted by the surface. And on the outside of the wall we have a bath of electromagnetic radiation. Generally, the electromagnetic radiation, the light observed from a body, is a combination of light emitted by that body and light that is reflected at that body. By definition, in this case, we want to consider a black wall, a black body wall, where reflected light is neglected. In other words, all the light that is incident is absorbed, and light that is coming from the surface, from the black body, is emitted. It's due to the motion of a charge carrier inside that creates an electromagnetic wave. Reflection does not take place. A black body may thus be defined as an object which fully absorbs all incident radiation, and only emitted radiation is observed. This cannot be readily realized in the laboratory. In the laboratory, a perfect black body does not exist. However, a good approximation of this concept is shown at the bottom. A cavity with black absorbent walls with just a tiny hole to observe the spectrum of the light inside. The question what the observed spectrum inside might look like was among others asked by Max Planck in 1900. The next step in the development of this concept of a black body radiator cavity is the establishment of standing wave modes of radiation inside this cavity. The idea here is that as soon as a constant temperature is established, as soon as thermal equilibrium between walls and radiation occurs, the absorption of light at the wall will equal the emission of light from the wall. Furthermore, inside the cavity, the light waves will interfere with each other, and this will occur in a constructive or in a destructive way. The important realization here is that only light waves that have nodes on the walls, where the amplitude does not change on the wall, standing waves inside the cavity, will constructively interfere and will be maintained. Waves with wavelengths that do not allow such standing waves will destructively interfere and diminished, and they will not be present. This distinction between standing waves and others is really important because this is how quantization enters the picture. Not all frequencies are allowed inside the cavity, only those frequencies that permit standing waves. Similar to a guitar string, once standing waves are established, one can count the modes. There is a fundamental mode, a first order harmonic, a second order harmonic. The same idea applies here. One can also ask the question, what happens if the frequency changes? And it becomes quickly apparent that for higher frequencies, more modes can be fitted into a cavity like this. This is illustrated on the left. Let's say for a frequency f3 we can fit in 3 modes. If we now double this, as illustrated at the bottom, it's possible to fit in more modes, say 9. Mathematically this can be worked out, and without proof we might accept that the number of modes that can be fitted into such a cavity is proportional to the frequency square. In fact, considering the geometry, it is equal to 8 pi on speed of light cubed times frequency squared. In the solid walls, the energy of the radiator is carried by the microscopic motion of the molecular constituents. What carries the energy inside the cavity? That would be the modes of radiation. So the next obvious question in the development of this concept is, what energy is carried by each mode? In the classical approach, before Max Planck's important realizations, all modes are considered to be equal and carry the same energy, which is given by the product of Boltzmann constant and temperature, kBT. This is also referred to as the equipartition or the equal distribution of the energy. The energy density or the intensity of radiation, dE with respect to dF, is therefore equal to the product of the number of modes times this equipartition energy kBT. Taking the result from the previous slide, namely 8 pi on c cubed times f squared, and multiplying this with kBT, one obtains the Rayleigh-Jeans radiation law. It is apparent that this energy density increases parabolically with frequency, with f squared, and that is shown in the plot at the bottom, which shows the energy density as a function of frequency. The theoretical prediction, dashed, increases and goes to infinity. This reproduces the data, the measured data, only for the very low frequencies. Because of the discrepancy at higher frequencies, this was referred to at the time as the ultraviolet catastrophe. Theory and experimental measurement did not agree for high frequencies. It was not possible to explain the observations with the classical physics approach. This view graph shows the comparison of the classical equipartition and the modern quantization approach that was developed by Max Planck in 1900. Since theoretical physics was as a dead end, everything was possible to overcome this problem. And one might say he decided on some different accounting. In the classical Rayleigh-Jeans approach, all modes carry the same energy. However, with increasing frequency, the number of modes increases. I've indicated this here by plotting the number of modes on top of that constant energy. Max Planck decided to account for those states differently and give them different energies. That's illustrated by the dashed rectangle. One such dashed rectangle for one frequency is shown on the right. The modes are now spread out in energy. Each mode has a different energy, and the difference in energy is defined by a constant of proportionality, h, times that frequency. So they are spaced equally, but they don't have the same energy. Since the integer n that labels the modes runs into infinity, this would be energetically not possible unless the population of these states is controlled in a finite fashion. Planck achieves this through a weighted occupation Boltzmann distribution. As shown, the modes with low energy are not heavily populated. At higher energies there is a larger population where the distribution has its hump, and then towards even higher energy the population decreases again, so that the population as a whole is finite and energy does not run into infinity. Both approaches, classical and Planck's approach, have in common that the number of modes is given by 8 pi on c cubed times frequency squared. However, two important differences occur. In the classical Rayleigh-Jeans approach, the modes are equally populated, whereas in Planck's approach, the modes are populated in a weighted fashion, in agreement with the factor 1 over e to the power of hf on kBt minus 1, which is given on the right. The second difference is that classically each mode has the same energy kBt. In Planck's approach, the energy associated with each mode increases with n, the label of the mode. The energy associated with the radiation is then due to quantum jumps between those modes, and is given by Planck's constant h times frequency. At the bottom, the two equations for the energy density are given. On the left, as pointed out before, the Rayleigh-Jeans equation is parabolic with frequency, leading into the ultraviolet catastrophe. On the right, Planck's equation, in which the energy density is given by 8 pi on c cubed times hf cubed divided by the Boltzmann factor, e to the power of hf on kBt minus 1. This function mathematically represents a hump. An increase with frequency leads to a maximum, beyond which the function decreases again to 0 in infinity. This corresponds to the observed intensity function. As illustrated at the top, expressing the energy density as a function of wavelength rather than as a function of frequency brings in a factor of c, the speed of light, divided by frequency squared. The Rayleigh-Jeans law then becomes 8 pi on lambda to the power of 4 times kBt. Considering also that radiation goes in all directions, brings in a further factor of c on 4, so that in the Rayleigh-Jeans version, the intensity law as a function of wavelength is given by 2 pi c divided by lambda to the power of 4 times kBt. Making the same changes, Max Planck's radiation law in its final form is given by 2 pi on lambda to the power of 4 times Planck's constant h times c squared divided by lambda times the Boltzmann factor 1 over e to the power of hc divided by lambda kBt minus 1. This slide shows the application of Planck's radiation law to different types of hot bodies. for example the Sun's surface at 6000 kelvins, a red-hot object like a piece of steel pulled out of the furnace at 1800 Kelvin, the Earth's surface at room temperature 300 Kelvin, and the cosmic background radiation at 2.7 Kelvin. It is apparent that the shape of the curve is always the same. What changes with temperature is the wavelength range in which the radiation is most intense. For the Sun, the most intense radiation occurs over the visible range between 400 and 700 nanometers. In the case of the cosmic background radiation, the most intense radiation occurs over a wavelength range from 0.5 millimeters to about 3 millimeters. The significance of Planck's radiation law from 1900 cannot be underestimated. Not only does it explain the black body radiation, it has many applications. It shows us that the universe as a whole is a huge black body cavity. It explains the radiation emission from sun and stars and confirms that they are approximately black bodies. Fundamentally, the radiation law introduces quantization to physics. This is because it contains the Planck action quantum h equals 6.626 times 10 to the minus 34 joule seconds as a universal constant to physics, which is the most important physical constant of microscopic physics, of quantum physics. Planck's radiation law shows us that the energy of the modes in a black body cavity is not all the same, but that it is quantized, and that the emission of photons occurs through quantum jumps between those modes. The sketch on the left shows the intensity curves for different temperatures. If a temperature is high, the intensity curve is large and has a large integral. If the temperature decreases, as for T2 and then further for T3, the intensity curve shifts to larger wavelengths and the integral becomes smaller. This is quantified by two additional important laws of physics, the Stefan-Boltzmann law and the Wien displacement law. The Stefan-Boltzmann law tells us that the integral under the curve is equal to the total power emitted by the black body radiator, and it's given by sigma times A times E times t to the power of 4, whereby sigma is the Stefan-Boltzmann constant, A is the surface area from which the emission occurs, E is not the electric charge but the emissivity of the surface, which for an ideal black body is equal to 1, and importantly, the power goes with the temperature to the power of 4. So a slight increase in temperature results in a huge increase in emitted radiation power. As temperature decreases, the distribution of intensity shifts to the right, to larger wavelengths. This is quantified by Wien's displacement law, which says that the wavelengths at which the maximum of the intensity curve occurs is always given by 2.9 times 10 to the minus 3 meters Kelvin divided by the temperature T in Kelvin. Thus, by measuring the black body spectrum, the temperature of a black body can be determined. Not the least, the radiation law was historically important because Einstein was inspired and developed from this the concept of the photon HF. Fundamentally and microscopically, Planck's radiation law and its good agreement with black body radiators in nature demonstrates that the emission of radiation is not, as it is predicted classically, like illustrated on the left, a charged atom or charge carrier that oscillates and then gradually slows down while an electromagnetic wave is emitted. That's not how radiation is emitted. Instead, it occurs when an oscillator, a charged oscillator, changes its mode. when it goes from a higher energy mode into a lower energy mode, then an energy quantum is emitted, a photon. This is how the radiation is generated. So instead of a gradual emission of radiation energy, energy is irradiated in discrete steps, in quantum jumps. The quantum oscillator is then pumped up again by the heat energy of the black body, so that thermal equilibrium is maintained.